Alright guys, I'm back, and now I'm gonna explain this correctly. Because I felt like I was gonna go off in the incorrect moment. So, let's get into this. So, we're given this list of sorted items. Correct? 1, 2, 3, 4, 5, 6. What would be the fastest way to implement it? Since our height of a tree is like base 2 of n. So, we know this is sorted. Where would we start off our hat at if we want this to not look like this? So, this is what happens when your tree isn't properly created. So this is still sorted, but not in the way. It won't be a binary tree. This will just be a linked list. Because like 1, 2, 3, 4, 5. That's just a linked list, guys. So we want to start off in the middle. In this middle part, well, there's the start. So there's our start. There's our end. And we're getting the middle point. Now, to create this, you can either do it iteratively or recursively. I recommend recursively because you're able to see much. You're able to manage more. So, let's create our tree. We want to start off at the middle point. Okay. So let's call our function. We start off at 3. Okay, we already called our function. We're going to start it off at 3. So our midpoint is 1, 0, 1, 2, 3, 4, 5. Our midpoint is 2. Now, what we're going to do is we're going to make this our kind of like our root. Correct? So this will be a root. From that point on, we're going to recurse through our linked list. So, wait, is this my midpoint? 0, 1, 2, 3, 4, 5, 0 minus 5 divided by 2, wait. I did the math wrong.
Yeah, it's 2.5, which is just 2.
Alright, just making sure. So we're gonna recurse through our function. Let's call tree node again. Okay, so when okay, let me rephrase this. So we have our root. Now we need our left and right. Do you know how to get that? Alright, good answers. So, you would create, or you would call your function recursively and set your tree left, or whatever you have it as, your left is going to be equal to this part. So that will be your left. And your right will be equal to this part. And then at this point, you're going to get your mid. So this is going to be your mid. My mid here is going to be equal to 5. My mid here, 1 divided by 2, that's 0. That's going to be 1. Right? 1 divided by 0, 1 divided by 2. That's 0.5. So, my tree is going to be looking like this, 1 and 5. Now, we call the function again, and this changes. So, we're going to change this. Well, when you call again, you're recreating these guys. You're reassigning them. So, at this point, we have 1, and our starting point is going to be, I believe, 1, And then our ending point is going to be 1. Alright, is that the correct math? Okay. I mean...
You said for the ending, the starting point is 3?
Yeah. Alright. So 1, 1. This is just going to become a, you know, your tree. What position would it be located at? Because it's a start, mid, -1. So... So this is just gonna be 2, and it's gonna be located in. Why? Oh, okay. Why is that in the? Not in the left. Not in the left. Not in the left. Not in the left. It's gonna be because you add your med +1. This is a 2. 2 minus 1 divided by 2. Okay, now I'm horrible at math here right now. I hope Dr. Charlotte doesn't watch this one. He told me he watched another one of them, and I'm like, yeah, I didn't explain that one so good. I'll remake them, don't worry. So right now, your midpoint is this one. And your right. And I believe this is your right. Yes, this will be your right. Main reason because there's nothing on the left side of the 1. So this would be your right side. So it's just 2, and your left side would be just nothing. Just put it as no pointer. Now we would make this one a 2, and then this one would point to null. Now let's go to this one. So 5. My left side will be 4, and my right side will be 6. But do you guys kind of get the gist of what I'm trying to say without the math involved? Because right now I'm not thinking of math.
Yeah, to make a balanced binary search tree, given the parameters.
Yes. So you're always going to start off at the middle on your when you first call your function. Start off at the middle, and your left side will be start. Your start is going to be, start, and then your mid is going to be at mid -1 for your left side. So let me just...
Basically,
Yeah?
basically all we're doing here is first we find the middle, and then from there we go down the row, and from there we put them in their appropriate place, right? And left and right.
Yeah. Yeah, because this is your root, and this is your start, this is your end. And we're going to start it off. We already have this as our tree, as our root. Now let's branch out. This is our left side. This is our right side. And we want the mid. We want the middle point. So this becomes our... I believe this becomes our mid. And then we branch out again. Let me see if I'm illustrating this correctly. So this one's gone, this one's gone, this one's gone. And we branch out again. So this is our left. There's our right. There's our left. There's our right. And then we want the middle point. And let's say this is already it. There's our middle point. And when we go further, yeah, and there's another middle point here, goes here, goes here. So it gets the middle point, creates it, and checks the left and right. So does that make sense? Oh my god, there's a horrible explanation.
I got it.
Alright.
Yeah, it makes sense.
You're just recursively doing the same thing until you run out of metals too.
Yeah, you're doing the same thing. Now, for level order traversal, this one's fairly simple. You're gonna be using the standard library queue. Do you guys know what that is?
You're talking about the third question?
Yes. So just your standard library queue. That's the library they offer you. You can use it. It's the homework assignment. I believe it does state that you can use it. So let's say this here. Hint: you may use the standard library queue in your solution. So remember the tree that we created last time? You're gonna be recursing through it. Not well, yeah, you can recurse through it. And iterate through it. So what we're gonna do is we're gonna iterate through the tree. So you guys know the gist of iterating, right? Let me erase this. I'm just gonna illustrate it like, hey, I'm here, and then let me do this. So what level order traversal basically means is that it prints out this one, it prints out this one, then 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 this one. So it goes like this, I believe, when it's printing out. Does it give you an image? Yes. So I don't know if the recording can see this. So basically you're printing out A, B, C, D, E, F, and as I illustrated, you're going to be working with this. Where is my thingy? Alright. Where's my replit? So what I recommend when doing this is always put your current node or your root first. So you have your queuing system. Put the first node that you have inside it. So push it. So this is my first node. Let's call it N1. And N1 contains data. So you're going to have a while loop, or you can iterate through it until there's no more nodes in your list. And because you know it's in a queuing system, you're always going to put in things. So print out the data that this thing offers. Get the children, or the left and right. So you first get the left one because you're starting off there, and then the right one. So let me do this. And one, because this one's fairly simple. I don't know how to explain it to you without giving you guys the answer. I'm just gonna do up to N4, and then let's say N5, N6, N7. So print out the data it contains, and then look at the left child. If it's null pointer, don't do anything. If it's not, input this node into your queuing system. So N2. And then check the right side. So you check this side and input it here, because you know it's not a null pointer. So you input it. Now that you've done this, remove the first item, because you already did whatever you could with it. So you erase it. Huh?
And what's that thing on the top? Is that like an array or like a linked list?
It's a queue. It's a queue.
Oh, we have to use a queue for this.
Yes, it's a. You have to use a standard library queue to solve for this problem. It's pretty simple. So you just create your queue with a node variable with whatever name, and basically what I'm inputting here are the nodes. So you can do insert node, push node, and once you're done using it, you pop it out. So
okay.
So right now I popped out my first node. Now node 2 is the current one I'm going to be looking at. So, as I said, the first one is deleted, so it's gonna look like this. This is not like technically correct, but just to illustrate it and make it look more nicely, I'm working with this right now because node 1 I already worked with it. I removed it from my queue, so right now I'm working with N2. Now you're gonna display the data, then check its nodes, left and right nodes. So this node has N4, so I put N4 into my queue, and then I put N5 into my queue. From that point, I will... What would I do at this point? I already displayed my data, I already checked my left and right. What would I do in this point?
It popped the left and then popped the right?
No.
No.
I would remove my N2 by popping it. So I remove N2, and let me just reorder the thing. N3, N4, N5. Now, where's my eraser tool? Now N2 does not exist when I'm trying to display the information. Now I have N3. What would I do at this point?
Get the children of N3 and then pop it?
What would I do first? Because this is a level order traversal print, so you're printing out this information.
Print out N3.
Yes, you print out N3, and then you go into the children and get your nodes. I mean, you can print out whatever point, but like it's just to emphasize that you should print.
So you print after you pop them out of the queue, or you print before you send them into the queue? 'Cause that last part confused me.
For my implementation, you can print out at any point because it's in a queuing system, and I just call my queue at the front and display the data because this data is still here. I just call it and display it. It should still be in order because I don't look at this child's data. I don't look at this child's data. I'm looking only at this one. So depending on your implementation, how you have it, because there's level order, there's what are the other ones? Because there's
The pre-order, in order.
yes, you have those different types. So if you're doing this in a recursive form, as he's done before, the printing it out depending on where you have them located really matters. But for my implementation, I have this information stored in a queue, so it doesn't really matter. So always check the order in which you're inputting them or outputting them.
Okay.
Yeah. So just what I always recommend everyone is debug it, print it out, see what's happening, read your code, illustrate it yourself. So you have data, you looked at the left one, so N6, and you look at the right one, N7. I get rid of N3. And I think you guys get the gist of it now, right?
Yes, sir.
So at this point, so N4, N5, N6, N7. What do I do at this point? So this is a trick question. What would I do?
You check if the children are null pointers.
Yes. So does this node have null pointers? Does this node have children?
No.
So what do you do? Do you push anything in?
Print it out and pop.
Yep. You print it out and pop. So you print it out, it pops. You print it out, it pops. Yeah, you print it out, it pops. So
So if the children are null pointers, just print out the one on top, the root, and then pop it, right? And then you're done with that side.
yeah. So let me explain to you this in somewhat of a code. So you have your queuing system. You get the front of your queuing system because it is your front, and you display the information. At that point, look at the left or right child, and then pop your information. Because when you're checking for left and right, you want to check if it's a null pointer or not. And if it is a null pointer, don't add anything to the list. If there is a node, you add it. So, for example, if I have this, let's say that's 15, this is 16. I would display the information of 15 first, or you can do it last. Well, it really depends on how you have it structured, because you can do this recursively or iteratively. So it's one of the two. Unless, let me see, can you do this? I believe in this one. Yeah, you can do this recursively. I believe so. Yeah. If you want to do it recursively, you just follow Dr. Shoulder's example. So right here, he has some printed code recursively, and you just gotta make sure how you're messing with the information. But in this case, you have your queuing system here, 15. I pop this out. Well, not I don't pop out yet. So let's see here.
And when we find out that both of the children's are null pointers on the left side, we still have to check if both of the children on the right side are null pointers, right?
Yes.
Okay, and so how do you stop searching? Do you just do like a return?
Oh, so what is this?
Binary search tree?
No,
I mean,
no.
it's just a search tree.
No, what is this? What does it have? This is your queue. This is your queue number. What does it have right now? Because you already went through all the items as we did it, so right now it has nothing. Now, if you look at the standard library for a queue, there's this fun command called let's give it a look, guys. STL. Yeah, that's the fun. That's
Oh.
so. If the video records this, I believe it does. There is an empty. So just check if it's empty, and that would be it.
And that's when you return.
Yeah.
Okay, that makes sense.
All right. So let's see here. Yeah, just let. Oh my god, I have to do that. Oh my god. So yeah, that's mostly just it for the homework. So key things here that you need to take into consideration is that I'm gonna be redoing some of the videos. Main reason is because Dr. Schwoller looked at some of them, and I seen my mistakes, and he told me my white lie hint was incorrect. So I'm gonna be redoing those just so I can see if Dr. Schwoller will use them in the future. So that's mostly just it for today's session. Have a nice day, and goodbye.